spectrum, spreaded. So what's the spectrum spreaded? It shows the transparency of property of the communications, that it does not interfere with the narrowband communication systems that are already existing over there. Like it will be transparent to the AM receivers, and AM and FM receivers will be transparent to the spread spectrum signals receivers. So then I have talked about the basic features. Some features of the spread spectrum communication system, like immunity to jamming, low interference, high processing gain, which is simply defined as chip rate divided by the information bit rate. And then obviously there is an easy encryption because that we can do by using the PN sequence. And what is the PN sequence? Basic introductions about that also are given. That is the, simply in strict sense, if you talk about the PN sequence, it is deterministic in nature, but the period of the repetition is very large. So we consider it as, all our calculations, we consider it as a random signals. And it is nothing but the high chip rate. What is chip rate? I will let you know. High chip rate, NRZ data. That's it. And it provides the greater security, multiple access techniques like CDMA is possible, and then it is registered to the fading cache by the multipath effect. Some applications also are discussed that it is being used in the military communication system, police radar, satellite communication server, telephony, GPS, Bluetooth system for multiple access and many more. Then I had discussed about the types of spread spectrum techniques. Like there are mainly 4 types. One is the direct sequence spread spectrum, frequency open spread spectrum. Third one is the time open spread spectrum techniques. And then fourth one is the hybrid system, which is the combination of any one of these two, and especially for case 2 and case 3. Now, we are going to discuss a little bit introductions about this direct sequence spread spectrum, which is the first time of spread spectrum techniques are already discussed. Little bit introductions, but again, I'm starting this class from the discussion of the direct sequence spread spectrum. So as I told you, that spread spectrum technique is the modulation of the modulated signal. So if in the first stage, if you suppose we take the BPSK signal, if in the first stage, if we take the BPSK signals, and then after this BPSK signal, if we again amplitude modulate, that is the second time modulation. If we do with the amplitude modulation, actually, if we do the amplitude modulations, and that amplitude modulation system with the help of PN sequence, then it is called as direct sequence spread spectrum. And we'll see later on that how just by multiplying the PN sequence to the BPSK signal, which it gives you the amplitude modulation second time. That is amplitude modulation in the second modulation causes the spreading of the spectrum. So that is called as direct sequence spread spectrum techniques. So a direct sequence spread spectrum signal is one in which the amplitude of an already modulated signal, which is the already modulated signal, BPSK signal is already modulated signal, whose amplitude we again modulate second time with a very high energetic binary stream of the digits. And this high rate energetic binary stream of the digit is nothing but the PN sequence. Okay, so this is the basic definition of the direct sequence spread spectrum. Now we will see what are the things we are going to study in this direct sequence spread spectrum. We will see that how can we generate this spread spectrum techniques, the DSSS, and then how can we regenerate our original message signals from the DSS, and then what is the effect of the noise in this DSS if we consider the white noise simply, that is the thermal noise, and what will be the effect in communication, that is what will the bit generate if we consider the deterministic signals as an interfering signals, which is the single tone interfering and jamming. So these things we will be studying in the direct sequence spectrum techniques. So in this, suppose thus our original signal ST is what will be ST hour, because we are considering the original signal. Although our original signal is TT, that is the data which we want to actually spread, but first this data gets modulated using the BPSK techniques. So our original signal ST we simply consider as the BPSK signal. So this is the mathematical representation of the BPSK signals, which you must have already studied in the previous model. That is not in the previous model, in the model 3. So ST is given as under 2PS. PS is the signal power. DT is the data, digital data, which we want to transmit using the BPSK signal. And this cos omega naught t. So we know the basic property of the BPSK that whenever this GT is 1, this BPSK in the BPSK we simply transmit the carrier signal cos omega naught t. So whenever the DT is 1, this which is represented by say plus B board in the NRZ representation, then ST will be simply under 2PS cos omega naught t. We simply transmit the carrier signal. This is the carrier frequency. Now, if there is a 0 which is represented by minus b board in the energy representations, then minus b board once it is multiplied over here in place of this dt, if we place it, keep it as a minus b board, then this signal will be minus under 2ps cos omega naught t, which we can write it as under 2ps cos omega naught t plus pi. It means that we are sending the carrier signal with 180 degree out of phase, which is the thing about BPSK signal. BPSK modulation techniques. So this ST is nothing but the BPSK signals, which here we are considering as an original signal, because as per the definition of the spread spectrum signals, that is the modulation of the modulated signal. So we are considering the modulated signal as the BPSK signal. Now, in direct sequence spread spectrum, what we do? The already modulated signal, this one is the already modulated signal, is amplitude modulated. Now we are going to amplitude modulate this signal by a very high bit rate, a high rate NRZ binary stream data, which is nothing but the PN sequence. So how can we this modulate the amplitude? How can we amplitude modulate this modulated signal? Just by multiplying over here the PN sequence. So this PS is the signal power, as I told you, and this is nothing but the banded PSK signal. Then the DS spectrum signal will be how much? Just by multiplying this with the high rate NRZ binary stream, which is called as PN sequence, which is denoted by GT. So the DS spread spectrum signal is simply represented by GT multiplied by this ST, which we can write it as under 2PS GT cos omega naught t. Now, so this is the mathematical representation of the BPSK signals, and this is a mathematical representation of, we can say, the direct sequences for spectrum signals. We will see later on that how can we generate this signal, okay, and how can we detect our original message signal, original data DT from this DS spread direct sequences for spectrum techniques, modulated signal. But it is better to understand these two with the help of some graphical representation. So this GT, as I told you, is nothing but a pseudo random noise code binary sequence having the value of 1, plus 1, and minus 1. It is called as the random. In all mathematical calculations, we will be considering random only, but it is not in fact the random. In the instructions, it is deterministic, whose period of the repetition is very large. Okay, and it is represented simply as a binary digit, which is having the value of plus 1 or minus 1. Right? Like 1 is represented by plus 1 board and 0 is represented by minus 1 board, simply. Okay, so this is nothing but the NRZ data, simply. Okay, now if we talk about the graphical representation, then it will give you the clear understanding that what is actually this signal. Okay, this is our DT. This is our DT. DT is the original data, digital data which we want to transmit. Right? So this is DT. If I ask you to draw the waveform for this under 2ps DT cos omega naught t, then you can simply draw that if there is a 1, then there will be a carrier signal. If there is a 0, which is represented by minus 1 volts, say this one is plus 1, this is minus 1 volts, then here we can change the carrier phase by 1 degree. So that will be the representation of this ST. Now, but we are not concentrating the representation of the ST like the inclusion of this cos omega naught t. Rather, we are actually focusing over there that what will be the nature of this DT. If you consider DT is that, and if you consider some specific GT, then what will happen? So this is the DT we have considered. That is 1 and 0. 1 is represented by plus 1 volt, 0 is represented by minus 1 volt. This is also represented in the energy data. Okay. Now, here we have considered, and one more thing, this DT, we consider the bit rate as FP. That is the number of bits in per second period is nothing but FP. So bit rate of this DT is considered over here as FP. Now GT is again I just told you that GT is the pseudo random noise code which is represented by this one, okay. But if you look to this graph, as I told you that this GT is nothing but the high rate energetic binary stream. That's why it is having the high rate energetic binary stream whose bit rate is represented by FC. Okay. So now this is the high bit rate. Now since here in this case, like in the DS spread spectrum signals, this GT, which is nothing but we are multiplying this GT with the ST. So here we have the term GT and GT with the DT. So let us see what will be the nature of this GT into DT product, GT into DT. So you can see if you multiply this GT with the GT, so wherever there is a 1 will appear. Wherever there is a 1 and -1, the -1 will appear. And here also 1 -1 will appear. Hence, if you talk about the bit rate of this multiplied signals, that is GT into DT, so bit rate of this one will be nothing but FC, because the position, the bit is changing according to the pseudo random noise code. Okay, so the bit rate of this one will also be FC. Now, I'm going to tell you one important term, that is, if you consider this DT, then since DT is the original message signal which is represented by the energy data whose bit rate is at B, we call it as bit rate. But to differentiate this bit rate with the rate of this pseudo random noise code, we represent this FC as a chip rate, not with the bit rate. And the meaning of this FB and FC, the basic definition of the bit rate will remain same. That is, the definition of the bit rate is same to that of the chip rate. Only the difference is in the nomenclature. That is, in the case of original message signal, represented by the bit rate is represented by FB. Yeah.
Sir, very sorry to interrupt, sir, but now we have MLM class, sir. There is a slight change in the timetable, and DComm class have been shifted to 12 o'clock.
Who has shifted the digital communications class?
Sir, Karthik Mahato, sir. Now we
ask the Karthik Mahato. You please ask the Karthik Mahato, sir, that I am not ready to shift the class.
Yes, sir.
Because no one has informed me. Okay.
Yes, sir.
Please be connected in this class only. I will be talking to Suvangi sir, because neither Karthik sir has informed you, neither you people have informed me, and that is not in fact your job. I should have received the information from the department itself.
Okay? Sorry, sir. Karthik sir informed us, but because of the habit, we forgot.
No. Karthik sir has informed you. It's okay. But since I have earlier scheduled class now.
Yes, sir.
So don't worry. You be connected in my class. After this class, I will be talking to Karthik sir, and I will also talk to Sulanki sir. Okay?
Yes, sir. Thank you, sir.
Okay. Thank you. So I was talking there. Here. So I want to tell you that this FB, which we call it as bit rate, in the case of this DT, energy data, okay, but this basic definition of the bit rate and chip rate remains same. That is how many number of bits we are transmitting in 1 second, and how many number of bits here also we are transmitting in 1 second. But in case of energy data, which is the message signal DT, we call simply as a bit rate, whereas in the case of this pseudo noise random code, we call it as chip rate. Why we call it as chip rate? Because the chip terminology is coming from there only. That is, this GT chops this DT in various chips. That's why this chip rate is used. This GT, once we multiply this GT with the DT, this GT chops this DT in various chips. That's why we call. And what is the chip rate? That is nothing but the FC. That's why we call this FC as a chip rate. And also to differentiate the two terminology, that is FB is the bit rate and FC we call it as chip rate, which is very high. So whenever we talk about the chip rate, that chip rate is very, very high as compared to the bit rate, right? So that's why we take the two different nomenclature, although the basic differences remain same. That is how many number of bits are transmitted in per second. That is nothing but the bit rate, and here we call it as how many chips are transmitted, and the bit and chip both are same. But the chip duration is very small. That's why chip rate is very large, and bit duration is relatively large. That's why the bit rate is small. Okay, so this is FB, FC, and FC. Now, But one thing we must have to note over here, that this will have exactly the same chip rate what we have at the GT. If the transition, wherever there is a transition in the DT, remain matching with the one of the edges, remain matching with the transition of the pseudo as random code. If this happens, that is, if suppose there is a transition and here there is a transition, if these two edges will match, then this FC will remain same, the chip rate of the DT into GT, which we actually try to maintain it in the spread communication system, spread spectrum communication system. Okay, so this is VT. So again, I'm going to actually just give you the slide actually recap, that this direct sequence spread spectrum is nothing but the modulation of the modulated signal, and the first modulated signals we consider as a PPSK signal, which is represented by under 2 PSTT cos omega naught t, and the second modulations which we do as an amplitude modulation signals is simply multiplied with the pseudo random noise code GTST. This pseudo random noise code is having the chip rate FC, which is much higher than the bit rate FB. And after multiplications, the signals what we are getting, that is GT into DT, that one also having the same chip rate as to that of the pseudo random noise code GT. And later on we will see that how can we multiply. And here one more important, I want to one more property for the PN sequence I want to highlight, that if we multiply, this is GT, if we multiply GT by again with GT, then what will happen? If we multiply GT with the same GT, then what will happen? Wherever this GT is 1, the signal will be 1 only. Wherever GT is -1, again this GT is -1, that signal will be 1 only. So here also the signal will be 1 only. So multiplication of GT with GT will not will come out to be 1 only. That is whether the whether the original GT is 1 or -1, the G square T will always be 1. And this property will be using later on while the generation of direct sequence spread spectrum, not in the generation, rather in the detection of the direct sequence spread spectrum. From here also, if I say that how can we generate this signal, then generation of the signal is very easy, because we know that we have already generated this BPSK signal, that is there is a NRJ data DT, and if this NRJ data is multiplied with the under 2 PS cos omega naught t, then we have the BPSK signals. Now, if the later on, if we again multiplied with the GT, that is the PN sequence, pseudo random noise sequence, then that will be nothing but our VT. So the generation of this one is very easy. You can simply generate just by generating the BPSK, and then just by multiplying this BPSK signal with the PN sequence. And in fact, the regeneration, that is the detection of this GT, is also very easy, because once this signal is received, if you multiply these signals with the GT itself first, then what will happen? If you multiply this signal with the GT, now we are talking about the detection of the signals. If you multiply these signals by the GT, then here it will be G square T. And we know that G square T is nothing but the 1. So the value will be nothing but, that next signal will be nothing but a BPSK signal. And we know that how the BPSK signals can be demodulated. That is just by using an integrate random circuit and making over here the decision making device, we can get the DT. So this is simply the generation and detection block diagram. So generation and detection block diagram of the direct sequence spread spectrum technique is also very easy. That is, just by multiplying this GT with the BPSK signals, we can have the spread spectrum. And after that, once this signal is received, first we multiply with the PN sequence. That's why I told you that until and unless we don't know exactly the same PN sequence what we have used at the transmitting side, we cannot recover our original information signal GT. So the use of this GT at the receiving end, which must be same what we have taken at the GT. So this also provides the better encryptions, and the security while transmitting the information. Now, another question arises, that how the spreading of the spectrum is possible. How the spreading of the spectrum is possible? Because ultimately what we are trying to do is to spread the spectrum. So if we see the spectrum of this signal, then power spectral density, this is DT. So DT is the energy data. You might have already studied in model 3 that energy data power spectral density is nothing but the sink square function. Sink square functions. right? Now sink square functions get multiplied by the cos omega naught t. So this sink square functions will be shifting to omega naught and minus omega naught. Okay, and it will have the bandwidth of how much? Bandwidth is determined by the bit rate of this GT, which is nothing but the FP. So FP is the bit rate. So this will be, this width will be nothing but twice FP. We all know that the bandwidth of the BPSK signal is twice FP. Now, what will happen in this case? What will happen in this case? In this case, we have to find out the power spectral density of GT into DT. And we know that GT and DT is nothing but again NRJ data having the chip frequency of FC, or we can say bit rate of FC. So its power spectral density will also be sinc function, sinc square functions. But that sinc square functions will shift to FC, shift to FC. That will be shifting to omega naught again. But this width, bandwidth of that spectrum will be nothing but twice FC, because the bit rate or chip rate of this GT and GT is nothing but the FC. So the bandwidth will be twice FC, and the bit rate or chip rate of this DT is nothing but the FB. So the bandwidth is twice FB. So now, as I told you, that FC is much greater than FB. Hence, this spectrum is much higher than this spectrum. So we are getting the spreading in the spectrum. So it is called as, it is the spread spectrum techniques. So what we see from till now discussions, that is, the generation and detection of the direct sequence spread spectrum technique is very easy, and at the same time it provides the better security, because until unless we don't have exact GT, and this GT is, although it is determined in the deterministic way, that is just by using our deterministic electronic circuitry, but since the period is long, so for all applications we consider it as a random signals. So since the random prediction of the random signal is very difficult and no one can actually spoof, that's why this will have the higher security and the secure informations we can transmit. And at the same time, it will not have any and later on we will see, and at the same time it is not getting received by another narrowband receivers like AM receivers, FM receivers, even though we are using the same frequency band because of the spreading of the spectrum. And third one we will talk about later on, that is, if we talk about the bit rate, that is error bit rate, then that bit error rate in this particular direct sequence spread spectrum, and if we talk about the Gaussian noise or thermal noise, then during the transmission, the thermal some noise may be added in this. And suppose the nature of this noise is nothing but the thermal noise whose power spectral density is eta by 2, then what will happen? This dt multiplied by under root ps cos omega naught t gt. Here we have the ds direct sequence spread spectrum signals. Once it is transmitted in the channel, some noise may be added. And once it is received, then what will happen? This signal is received along with the noise, say NRT. Noise signal is received. Now, once this signal is received, and in the first stage we are multiplying with the GT, then here in these equations, the GT will be multiplied, and at the same time with the NRT, the GT will be multiplied. So NRT, this GT will be multiplied. Then what will happen? And these signals, once it again multiplied by the BPSK receivers, that is, if you multiply with the same carrier signals under 2 cos omega naught t, and then by passing using the integrated dumb circuit and the decision making device, we can detect original message signal DT. But here NRT, which is the noise source, gets multiplied by GT. Then what will happen? NRT is the random noise source, which is multiplied by the GT, that which is having the high chip rate. Then ultimately what this GT will do, it will simply reverse the polarity of NRT. That is, wherever there is 1, it will reverse the polarity by -1, or there is plus before over a certain time period, it will reverse it to the minus, like that only. Either it will reverse the polarity or it will not reverse the polarity. Only that will happen. And we know that this one is the additive wide Gaussian noise. So the reversal of the polarity does not affect on the power spectral density. And at the same time, At the same time, it will not affect the probability density function of the wide Gaussian probability density function of the Gaussian function, because in the probability density functions of the Gaussian signals we see that it is 1 upon root 2 pi sigma square minus x minus mu whole square. Because of that whole square term, that is actually neglected. So this noise does not affect this noise power is not affected by the PN sequence effectively, we can say, and hence the bit error rate of the whole system, whole receiver, remains same to that of the bit error rate of BPSK signal. And we all know that bit error rate of the BPSK signal, or probability of error of the BPSK signal, is nothing but half complementary error function under root bit energy by eta. So this bit error rate remains same in the case of direct sequence spread spectrum techniques. So you can see how much advantages we are getting in the direct sequence spread spectrum techniques. That is, at the same times, we are not getting the high bit rate. First, we are getting the better security, right? Second, and at the same time, we are getting the lesser interference. The basic properties of the interference I will be touching later on. Okay, so this is all about the things what I have discussed about the direct sequence spread spectrum techniques. That is, in the direct sequence spread, I'm again repeating, in the direct sequence spread spectrum techniques, BPSK signals first we take, and then we amplitude modulate with the help of PN sequence, whose chip rate is very high as compared to the bit rate. The resulted signal DTGT is having the same chip rate FC, and because of that only there is a spreading in the spectrum. Okay, and at the same time bit error rate remains same, which is to that of the original BPSK signal. So suppose in any communications we are using the BPSK modulations techniques, so definitely that will after certain value the probability of error or bit error rate which we can, so that will remain same. That will remain same. So these are some features of the direct sequence spread spectrum. Now, so here we can say, here we merely assume that GT is a binary sequence as the data DT, and the sequence what I told you, I'm going to read it so that you can further have some idea. That is a sequence GT. This GT sequence GT is generated in a deterministic manner. I told you, no? It is generated in a deterministic manner and is repetitive. So if it is random in nature, then it will not be repetitive. But since it is generated in the deterministic manner, hence the period is repeated after a certain time. Right? However, the sequence length before repetition is usually extremely long, and to all intent and purposes and without serious error, we assume that the sequence is truly random. Right? That is, there is no correlation of R between the values of a particular bit and the value of any other bit. Right? Now, further, the bit rate FC of the GT, that is bit rate, here it is written, of FC of the GT is usually much greater than the bit rate FP. That furthermore, the bit rate FC of the GT is usually much greater than the bit rate FP of the DT. Right? This FC is much greater than the FP. As a matter of fact, the rate of the GT is usually okay. Right? So much greater than FP. So we say that GT chops the bit into bits of the data into chips. This GT chops the DT into various chips, and we call the rate GT as a chip rate. This GT as a chip rate. Okay, retaining the word bit rate to represent the FP. So FP is used to represent the bit rate. This bit rate is used to represent this FP, whereas chip rate is used to represent this FC. Now, it's a figure I've represented over here. Now, to see the multiplying the BPSK sequence ST by GT, spread the spectrum. shown you that how it spreaded the spectrum. We refer to the figure which shows that the data dt is a pseudo noise, often called the pseudo noise of PN sequence gt and the product sequence gt to dt. Now, note that the edges of the dt and gt are aligned. As I told you that edges of the dt and gt must be aligned, otherwise this fc will change. In the case of this gt into dt, this fc will not be same to that of the chiplet of the dt into ct if the edges are not aligned. Similarly, the product sequence is seen to be similar to dt. This sequence is seen to be very much similar to that of the gt. Okay, gt. The product sequence would be another random sequence g dash t. Suppose this one is the g dash t. So this g dash t having the same chip rate of fc as I told you. Okay. Since the bandwidth of the BPSK signal st is normally twice fp. Okay, as I shown that bandwidth of the BPSK signal is nothing but twice fp. Okay, and the bandwidth of the BPSK spread spectrum signal is nothing but the twice fc. Spread spectrum signal, it is nothing but the twice fc, and the spectrum has been split. Okay. Since the power transmitted by st and bt, definitely since the power transmitted this point I have not covered, since the point transmitted by st and bt is same, that is ps, hence the power density in this case in spread spectrum technique is reduced by the factor fb by fc, and we call fc by fb as a processing gain earlier. Okay, so if the processing gain is high, then fb by fc will be low, and then this power spectral density will be reduced by the less power amount. Okay, so this power spectral density is received. That's why we prefer to have the high processing gain. Another reason I will let you know later on also. Now, in more details, I have actually made this slide for the studying of this spectrum, and you can see that this is our spectral density of the energy data, that is of the DT, spectrum of DT, or spectral density of the spectrum of the DT. Now, another is this one. This is the power spectral density. This is ST, the BPSK signal. Okay, so what will be the power spectral density of BPSK signal? This signal, spectrum of this DT, power spectral density of this DT will be shifting to omega naught. So the spectrum, this will be shifting to omega naught, that is f naught. So this point will be f naught plus fb because this width is fb. Okay, so this point will be f naught plus fb, and this width will be f naught minus fb. So if the bandwidth of the data dt is nothing but fb, then the bandwidth requirement, transmission bandwidth requirement for the BPSK signal is coming out to be twice fb, as we all know. Okay, this width is twice fb. Right now, what will the spectrum? What will the spectrum? Which type of spectrum we will have for the direct sequence spread spectrum signal? Since the direct sequence spread spectrum signal is represented by under 2ps dt into gt, and the dt into gt having the chip frequency of fc, chip rate of fc, and gt and dt is nothing but the NRZ data, and we know that for NRZ data our power spectral density is this. So this power spectral density will be shifting to omega naught again, that is f naught. But as we know from the previous slide, that is this power spectral density will reduce. This power spectral density will reduce by the amount of fb by fc. So the peak of this one is reduced. Okay, and in this case, since this one is having the chip rate of fc, so this point will be fc, and this point will be minus fc. Hence, this point will be f naught plus fc. This point will be f naught minus fc. And if we talk about the bandwidth of these signals, then the bandwidth of these signals will be twice fc. And since we know that fc is much greater than twice fb, hence the bandwidth spectrum is spreaded. Spectrum is spreaded. That's why this is how we are getting the spreading in the spectrum. This also I have already discussed. That is, how can we generate the direct sequence spread spectrum and how can we detect? So generation and detections both are drawn in the same figure. So for the generations, this one is the transmitter. Okay, that is dt is the PN sequence. Dt is nothing but the energy data. Because this energetic data is multiplied by under 2ps cos omega t, because ultimately our aim is to generate this signal only, that is dt. So to generate these signals, first we generate under 2ps dt cos omega naught t, and then we multiply it by the gt. So this is dt, then under 2ps cos omega naught t, under 2ps cos omega naught t, this signal gets multiplied. So this is nothing but the BPSK signal. Now, if this BPSK signal is multiplied by the PN sequence, this is GT, this is PN sequence, this is PN sequence GT, then the output of this, we simply get the direct sequence spread spectrum signal. Now, this signal is transmitted in the channel. It may get affected by the noise, and we will consider the case of noise separately, considering the thermal noise and considering the deterministic single pole noise. Okay. Then this signal gets received at the receiving side. Okay. Then at the receiving side, we first multiply by the GT, as I told you earlier also. So once we multiply by the GT, it will become G square T, and the value of G square T is nothing but the 1. So ultimately, this signal will be converted to under 2ps dt into cos omega naught t, cos omega naught t. And this is nothing but our BPSK signal. So BPSK signal, here again we get BPSK signal. Now we know that how can we demodulate the BPSK signal, that is the received BPSK signal. First we multiply by under 2 cos omega naught t. So once we multiply it by the under 2 cos omega naught t, this will be PS cos square omega naught t. And this cos square omega naught t, we can write it as half 1 plus cos 2 omega naught t. And since we know this integrator is nothing but the low pass filter, so the lower frequency component, that is dt, half dt will come out. And if we take the sampling after each bit duration, then at the output we will be having nothing but the dt. And in fact, here you can also represent that integrator and the circuit and at the decision making device. Here decision making device is not mentioned over here, but ultimately at the last stage we must have to use the decision making device after the sampling, because after taking the sampling at each time period TB, that sampled value gets compared with a predefined threshold, and then if that value is higher than the predefined threshold, it decides that 1 has been transmitted, otherwise 0 has been transmitted. So correspondingly this dt is recovered. So that last part is not shown over here because that is understood. Although you can also write over here the BPSK receiver. So since BPSK receivers are BPSK detectors, BPSK demodulator, so the R remains same. So this is how we can generate and detect our DSS signals, direct sequence spread spectrum signals. Now, as I told you, we are going to consider the effect of the noise, and considering the effect of the noise, that also I have already told you that here what happens, if this signal is received over here, this is nothing but the direct sequence spread spectrum signals, then noise component is added over here. If you consider the effect of the noise component is added over here. When this signal is received at the receiving side, since this signal first multiplied by the GT, so this whole expression gets multiplied by GT. Then what happens at this point, because we have already discussed about this one, because this one is associated with the information signal DT, which will be recovered. And this noise, since we are considering the additive white Gaussian noise, so this noise NT is getting multiplied by this GT, getting multiplied by GT. And this GT simply changes the polarity of the NT, which does not affect on the probability of error, or which probability of error, because the white Gaussian noise power spectral density does not affect on the change of the polarity. Hence, bit error rate or probability of error in this case remains same to that of the BPSK signal. So the same things I have written over here also. That is, this is our prob diagram, and the probability of error, this is nothing but the probability of error of the BPSK, which is same to that of the direct sequence spectrum sequence. Okay, so you can see the same things are written over here. That is, at normally random times the polarity of the noise waveform is reversed because just by multiplying the GT. But we don't know that at what time the polarity will be reversed, because this noise is random and this GT is also random. Okay, so that is normally at the random times the polarity of the noise waveform is reversed, and it is intuitively clear that the reversal has no effect on the power spectral density are the probability density constants of the Gaussian noise, and hence it will not affect the probability of error. Hence, both the signals and the statistical property of the noise are unaffected by the spread spectrum techniques, and the overall performance of the system is not affected. As in BPSK without a spread spectrum, the error probability is this, which is the same for the DSS, the direct sequence spread spectrum, which is same to that of the direct sequence spread spectrum. So this is the effect of the thermal noise. Now, so the first, in the analysis of the noise, first we have considered the thermal noise, that's the white Gaussian noise. Now, second, we are going to consider as an interfering signals, which is the single tone interfering signals and channel. Okay, so and all this we are knowing that EV is nothing but the bit energy and eta by 2 is the two-sided power spectral density of the noise. Now, next we are going to consider the noise and as a single tone interfering, and that is actually designed, so we call it as so single tone interfering signals. So single tone means what? Only one sinusoidal signals we are considering, and that will be acting as an interfering signals. Okay, so now we are going to do the analysis of that. Are the direct sequence spread spectrum signals? For direct sequence spread spectrum signal, suppose the direct sequence spread spectrum signal is transmitted. Suppose the direct sequence spread spectrum signal is transmitted, and during the channel it is getting interfered by the single tone sinusoidal signals. Then what will be the analysis of this whole system, and what will be the probability of error of the receivers? Like in the case of white Gaussian noise, we know that the probability of error is given by this one only, which is same to that of the BPSK signals. But in place of considering the this noise as an additive white Gaussian noise, if you consider this noise as a interfering signals as a single tone sinusoidal signals, then what will be the probability of error? That is our aim is to calculate in this particular topic. That is, if you consider the interfering signals as a single tone means only one sinusoidal signals will be there. What we will be considering, and considering that, we will be calculating the probability of error of the system. So how can we calculate the probability of error of the system? So I'm just going to give you the basic methodology that how we are going to calculate that one probability of error for single tone interfering signals. Okay, so the basic idea is that this signal gets multiplied. So first we will consider this noise NT as sinusoidal signals, so that the signal gets added with this direct sequence spread spectrum signals. And since this signal gets multiplied by GT, then it will be multiplied, the whole signal will be multiplied by GT, and then whole signal will be multiplied by under 2 cross omega naught T. And then after passing this low pass filter, what these signals we are getting, that we will calculate, right? And at the output of this low-pass filter or integrated term circuit and to that of the decision-making device, we will see that which term is related to the noise term. And based on that, considering that term, we will be calculating the power spectral density, considering that term. Okay, then that power spectral density will be actually equating with the eta by 2. Why eta by 2 will be equating? Because it is very easy to know. We know that the probability of error for the case of white Gaussian noise is nothing but half a complementary error functions under EB by n naught, EB by eta. And since if you are able to calculate this eta, that is the power spectral density for the single tone interfering signals, then equating that power spectral density with the eta by 2 and calculating this eta and putting the value of eta in this particular equation, so we can calculate the probability of error. So this is our whole methodology, following which we will see that how can we calculate the probability of error in the case of single tone interfering signals. Okay, so you can see, and how that probability of error, what is the analysis, what is the need for calculating this probability of error, because ultimately we will come to the conclusion that by varying which parameters ultimately we can decrease the probability of error or bit error rate. So this is very important for the secure communications. Okay, so Ultimately, we will be calculating one parameters that is called as processing gain. What I told you earlier also, the processing gain is very important parameters, and we will see that if the processing gain is high, then the probability of error for that particular direct sequence transfer system is low. So, making that factor high, we can actually reduce the probability of error. So that will be our conclusion finally. Okay. So again, I'm repeating that how what methodology we'll be using to calculate the probability of error. That is, here we will be adding with a single tone interfering noise signals, and that will be multiplied by GT, and then it will be again multiplied by under 2 cos omega naught t. Then after passing with the low pass filter, we will calculate that which signals we will be getting, and based on that signals, we will be calculating the power spectral density, and that power spectral density value gets equated with the eta by 2, because we know that the for wide Gaussian noise eta by 2 is the power spectral density whose probability density function probability of error is given by this equations, and just by putting in that we will be able to calculate the probability of error, and then then we will see that by varying which parameters this probability of error can be minimized, because we know that this complementary error function is decreasing function of these parameters. So from there we can see that by varying which, like by varying which, we can have the lesser probability. So that conclusion we will make in the next class. So for time being, thank you to all of you. Meanwhile, if you have any doubt, you can ask me. Otherwise we can end our discussion over here. Please.
In the new timetable, the DComm class is from 12 o'clock, sir.
Today's class.
Yes, sir. Today's class
Any
is
other change?
Yes, sir.
Any other change?
One second, sir. I'll just see.
Hmm.
Sir,
Today's class is from
on Monday 2:30 DComm class. On Tuesday 12
Monday
o'clock.
2:30. It is unusual time. Okay.
Yes, sir. Tuesday 12 o'clock.
Tuesday it is shifted from 11 to 12. Yeah.
Yes, sir.
Okay.
And Thursday 1:30, sir.
So Thursday remains same.
Yes.
1:30. Okay, I do not have problem to take the class from 12 o'clock, but at least department should inform me. No? So neither Karthik sir nor HOD sir has informed me.